What allows for rocks to come sliding down the side of a mountain or just rolling down as a rock fall is the same force that allows water that falls anywhere to be moving downhill. It's gravity. So the role of gravity in slope stability can't be stressed enough. If we look at these block diagrams here, the one that's on a flat surface without a slope, gravity acts vertically so the block will not move on a flat surface. Gravity is pulling everything in the direction towards the center of the earth. So if it's on a slope, gravity pulls the block at an angle so the block can move on an angled slope, always moving downhill. There's two components of that. There's the normal component. The normal component pushes the block against the slope. And then there's the shear component. That's the force between the block and the surface it's sliding on. The shear component pushes the block down the slope. If you've ever tried to build a sand castle on the beach, you are familiar with this concept. Consider how steep a slope can be and remain stable. There is this particular angle called the angle of repose. The angle of repose is the maximum angle that a slope can be at and remain stable. So if you're piling sand up, like the example here shows, the angle of repose is the angle that naturally forms on that sand. So the angle of repose will change based on the material that you're dealing with. So if it's sand, it's going to have a particular type of repose versus large boulders or very fine clay will all behave differently. So the type of material will dictate the angle of repose as well as the moisture content. So back to the sandcastle building example. If you ever were having trouble building a sandcastle, usually you could get your sand a little wet and it would hold a steeper angle, right? You can make cool castle walls as long as you got the sand nice and wet. But if you got it too wet, then that would cause the sand to flow along with the fluid. So it's just the right amount of moisture that allows the angle of repose to change. Some parts of the slope can be steeper than the angle of repose. The example of the talus slope in the bottom left-hand corner here is showing us that. So you can see where the line is pointing, there's a small alluvial fan there where it's given way, and you've got a tiny landslide there. And then if we look at the scoria cone in the bottom right-hand corner, coarse material can have a steeper angle of repose. So if it's larger material, more like gravel, if it's more angular, it's easier for it to stick together. That will all change the angle of repose. And this is important when we're talking about landslides, because we need to know what is the material, what's the amount of moisture, what's the maximum angle it can be at before it's likely to slide. Observe what factors control slope stability. The angle of repose for the material. Loose materials like soil may have typical angle of repose, but solid rock can hold steeper slopes. The amount of water is important. Adding too much water to loose materials can weaken them, but adding a little bit can help them adhere together. The rock is weaker if there are discontinuities that are oriented so the rocks can slide downhill. So the example on the bottom, fractures, cleavage of the rock, and bedding of the rock. So the way that the layers or weak spots in the rock are oriented can facilitate a slide. So if everything is angled like it is in this image, the surface will just break along those planes of weakness and slide down. If you had the opposite angle of the layers and the same shape of the hill, that would be less of a problem. It's only when the discontinuities are parallel with the slope itself that it causes a problem. Observing the different areas of this terrain, I'd like you to think about events that could cause slope failure. So we've got lots of examples around here. Change in land use could include deforestation, weakening the soil, or building towns that load the soil and change runoff patterns. Where water can puddle, that can trigger the expanding and compacting of clays, so that shrink, swell action of clay-rich sediment. You can also have overloading of the slope by piling material or building structures on top of already unstable hillside. So this is a big problem with building in areas that have really steep slopes and are prone to this type of mass wasting. Similarly, if you undercut a slope, meaning you put in something like a road at the bottom of a hill, or a river comes by and cuts into that slope, that can trigger landslides as well. So with high precipitation, overloading of the slope or undercutting of the slope, changes in land use, and then finally volcanic eruptions and sudden shock like that from an earthquake can trigger landslides. Interesting enough, you can have the opposite effect as well. The largest recorded landslide is at Mount St. Helens in the 1980 eruption. Just preceding the eruption, there were earthquakes that triggered a landslide. This massive landslide came down, and with that huge release of pressure from essentially the entire hillside coming down, the magma below was able to come up to the surface as that huge volcanic eruption. So landslides can actually trigger volcanic eruptions. If they're near a coastline, landslides can also trigger a tsunami if it's a large enough landslide. This is usually associated with underwater landslides. Here are several ways that slopes can fail. In the upper left, we've got an undercut cliff. This is from the Yampa River in Utah. The next one over is a landslide that was triggered by an earthquake in Alaska. In the bottom left corner, the slope was just too steep. So it passed its own angle of repose and triggered a landslide. This is in Tibet. And then the one in the middle on the bottom, this is a typical landslide, and this is in El Salvador. This is a huge one. The bottom right is a landslide that was triggered by an undercut slope. So you can see that where the road is put is right at the base of that slope. So they made the foot of the slope too steep, and that triggered landslide. Slope failures are classified based on 3 different criteria: the mechanism of movement, the type of material, and the rate of movement. For the mechanism of movement, you're talking about either a fall or a flow. If you're talking about a fall, this is a mass-wasting process whereby large rocks and smaller pieces of bedrock detach and fall onto the ground. In contrast, if the rocks are not falling, they are flowing. So you would get something like a rock avalanche. So a high-velocity, turbulent flow of rock, sediment, and soil that results from the collapse of a steep mountain front. So this can take the form of a mud flow or a rock flow. That gets into the type of material as well as the rate of movement. So let's go there now. Type of material. If it's solid rock, that typically means it's just falling straight off of a cliff or rolling down a hill. They're large, solid pieces that are falling versus an unconsolidated rock, unconsolidated material. It's not cemented together. It hasn't been very well compacted. It's more sediment, and so it's more likely to flow. Rate of movement, you can either have fast or slow. And interesting enough, it is either really fast or really slow. So the really fast are the ones that you normally hear about. A rock fell right off the side of a mountain, right, going at the pace that gravity will allow it to, or a landslide flowed down a mountain rapidly, a mudslide overtook a river system and flowed very rapidly, or examples of very slow movement you can't see with your bare eye. Processes like creep, C-R-E-E-P. This is the slow, continuous movement of material like soil or other weak materials down a slope. So normally you can't even see it moving, but you can see that the surface has been disturbed, or you can see that vegetation is responding. Sometimes trees will start to grow in a J shape in response to this movement of the soil. So again, the three main things that we use to classify slope failures: the mechanism of movement, it's either a fall or a flow; the type of material, it's either solid or unconsolidated; and then the rate of movement is either fast or slow.